So what we're going to talk about today is the section on compound interest. For those of you who took 105, this should be familiar information, in particular these two formulas. I'm going to explain them regardless, but basically compound interest refers to the interest accrued on some lump sum of money, whether you're investing money or you're paying off credit card debt, and the balance you have on the credit card accrues interest over time. But all of those follow these compound interest formulas. Now you may notice, so we have two different types of compounding. One of them I'm calling discrete. This may be, even for those of you who might have had my 105 last semester, this might be a different set of terminology, but I call it this to distinguish it from continuous compounding. You use discrete compounding, these set of formulas, whenever you are compounding annually, monthly, or whatever else. There's daily, there's semi-annually. In fact, I put all the examples I could find on the first page of the notes. I have annually, semi-annually, quarterly, and I have n equals 1, 2, 4, etc. next to them, and I'll explain what those mean in a second. But in either formula, you might see a repetition of variables. A here, and I wrote down what all the formulas mean. A is the future amount, P is the principal or present amount, R is the rate as a decimal, we'll see that with these two examples. N will be the compounding cycles, which gives a little bit more meaning as to what the n equals 1, n equals 2 thing means. Again, we'll look at that here. T is time in years, and pretty much the same variables are over for the continuous compounding column. Just notice that there's no n. The n is gone, and instead you have e here, and a slight swap of the variables. So instead of nt in the exponent, you have rt in the exponent. And e, remember, e is not a variable. E is a special number, just like pi. In fact, e is in the calculator, which is something we will utilize quite a bit. I also have, so this row, this is future value type problems. If you invest something right now, what will the future value look like? That's these set of problems. If you want to reach a certain value in the future, what value do you need to invest currently to reach that value? That's what this row would represent. And again, we'll go through all these problems and give a little bit more clarity as to what all this means, but that table, this table at the bottom of page 86 in the notes, pretty much summarizes everything above it. So let's go ahead and look at these first two problems from example 1. So problem 1, and the directions in particular say, find the amount that results from the given investment. So if you invest all this stuff, given all of these conditions, what's the future amount going to look like? So if anything, we have a future amount, so that tells us we use one of these two formulas. Now it says compounded quarterly. Now compounded quarterly, that would fall under the discrete compounding. And you might notice that from the list of types of compounding, you only use this formula whenever it says compounded continuously, and it will tell you that. So notice in this problem, if you want to foreshadow. But any other situation, if it does not say compound continuously, it tells you to use one of these two formulas, depending on whether you're looking for a future or present value. So we are in fact looking for a future value, and we found out that this is a discrete compounding problem. So that tells us to look exactly here. So I'm gonna go ahead and I like to just write down the formula just to have a basis. And so now that I have sort of a basis to start off with, Another thing I recommend is writing down all the givens. And so we know exactly what to plug in, where to plug it in at, and whatnot. So we're solving for A, that's what we're looking for, so we can find P, R, N, and T. So P is the present or principal value, that's the $100. The R, so R is the rate, and it seems to be at 2%. However, R needs to be a decimal. So in order to change a percent to a decimal form, you have to, well, you can divide the number by 100, or you can move the decimal place to the left twice, which would give you 0.02. This would be the decimal equivalent. N represents how many cycles that we compound in a year. We are compounding quarterly, so you might think how many quarters are in a dollar, or if you split up a year into quarters, that's 4. I also wrote it down on that list of various compounding cycles. This is N is 4, and that comes from the quarterly aspect of this. And then T, of course, that represents time in years. It says 4 1/2, so I'm going to go ahead and put that as 4.5. So 4.5. So these are our givens. And now that we know what the value should be, after converting them if need be, let's go ahead and plug them in one by one. So P is 100. 1 plus the rate here is 0.02 divided by N, which is 4. All of that raised to the parenthesis N, which is 4, times T, which is 4.5. And so from here, so the nice thing about these formulas is, well, once you figure out the formula, it's just calculator work. So in the way I have the formula written down, so if you follow the formula exactly and you put your parentheses exactly here, if you put it in exactly this way in your calculator, no more, no less, you will have order of operations figured out, and it should work out fine. So 100 parentheses 1 plus 0.02 divided by 4, close parentheses, use the caret for the exponent, open parentheses, 4 times 4.5, and I get 109.39. And since this is money, you should expect for the majority, if not all of these problems, to ask you to round to the nearest cent. So again, that seems to be, let's go ahead and write that down. That is 109.39. That would be your final answer. And so we'll go ahead and move on to problem 2 here, which is a fairly similar problem. So here it's just, they throw different numbers at you. They also give a different type of compound. Now they say compounded continuously. As soon as you see that, you should think, well, you should think this column. And you might be familiar, you might have heard this be referenced as PERT, the PERT formula, and that's perfectly fine. I'll probably refer to it as such throughout this section. We'll be using the PERT formula because we're looking for a future value and we're compounding continuously. So again, just like the previous problem, I like to write it down. And from here, we can write out the givens. So A is what we're looking for. We need to find P, R, and T. Remember, E is not a variable, it's a number. And we'll figure out how to implement E momentarily. So P here, the principal value is $70. The rate seems to be 11%, but we do have to convert that to a decimal and to move the decimal place over twice to the left or divide by 100. That gives us 0.11, and the time is 4 years. So now that we have all of the givens, we can go ahead and plug those in one by one. So P is 70, E stays as E, all of that raised to the open parentheses, 0.11, or yeah, 0.11 times 4. Let's go ahead and plug this all in the calculator and see what happens. So again, if you resemble the formula exactly, you won't have to worry about order of operations or plugging in to the calculator in a fancy way. So 70, remember E, you have to press second, and then the third button on the first column. You'll see it in blue there, E raised to the X. And you will get E, they'll put a caret for you, and they'll put an open parentheses for you. So we can start off with 0.11 times 4, close parentheses, and I seem to get 108.69. So 108.69. Because remember, we're rounding to the nearest cent, so the 0.689, the 9 would round the 8 up to, well, a 9. And so this would be the answer for the first example. So now we move on to types of problems that involve us, well, solving for the principal or the present value. So even in the basis of the example, it says find the principal needed. So it is telling you find P in this case. So we're going to be focusing on formulas that are in this row right here because we're looking for present values. And so keep that in mind as we go through these. So the first one from example 2, to get $200 after 4 years, 7% compounded monthly. So the wording will also emphasize the type of variable you're looking for. So to get this amount, that means that 200 will be a future value, and again would further emphasize more so for the word problems that come up. It'll be helpful to use the wording to identify which formula you would use. So we're on this row, and it tells us compounded monthly, which is a discrete compounding metric. So remember, we always use this column whenever it's not saying compound continuously. We only use this column when it says continuous. So we would use this formula in particular, so I'll go ahead and write it down. So notice the only difference, you don't have to memorize these as if they're separate formulas. Notice the only difference, A and P switch. So A and P switch to P and A, and then the exponent changes to negative. So they're not completely disjoint formulas. In fact, they're based off of each other. One's a derivation of another. So you don't have to memorize all of these as if they're separable by any means. They are very much related. They're the same formula, just solved for a different variable. But anyways, so from here we can go ahead and solve for A, R, N, and T. So the A in this problem, remember A is future value. To get $200, that would be the future value in this problem. 4 years, that would be time. 7%, that would be the rate, but we do have to rewrite it as a decimal, which would be 0.07. And compound monthly, so remember monthly is 12, there's 12 months in a year. So once you have all of these, you can go ahead and plug into each corresponding variable on the right. So A here is 200, then 1 plus the rate is 0.07 divided by N, which is 12. All of that raised to the parentheses, don't forget the negative, negative 12 times t is 4. And from here, it's just calculator work. So if you plug in everything exactly, including the parentheses, it should work out fine. 200 parentheses 1 plus 0.07 divided by 12, close parentheses, raised to the open parentheses, negative 12 times 4, close parentheses, and I get 151.28. And let's make sure that is what I should get, that is. And that would conclude the first part. Now we move on to the second problem from example 2. So as you may notice, it's just different numbers, different type of compounding. So again, it says to get this amount, that tells us that we're looking for a future amount, or we're looking for a present amount given the future value. So we're still in this row, and since it says continuous, that tells us immediately to use this column. So we're using this formula. So this is P is equal to A e raised to the negative RT. And again, as I mentioned before, with the relation between these two are also very much related. Notice you're switching A and P, and then the exponent becomes negated in relation to the other. So the relations are the same. If hopefully that helps you memorize a little bit better. But let's go ahead and solve for A, R, and T. All of the unknowns over here. A here is 50. That's the future value. The rate here is 10%, which we do have to convert as a decimal. That would be 0.1 or 0.1, whatever. In fact, I'll put 0.1, doesn't matter. So 0.1, and time is 1 and 3 over 4, which we're going to write that as 1.75. And once you have all of your givens here, you can go ahead and plug those in one by one. So the A is 50. Remember, E is just E, so it carries over. Raised to the parenthesis. Again, don't forget the negative. The rate is 0.1. That times 1.75. And again, it's all calculator work. 50, press E. It'll put all of this for you, and you start off with negative 0.1 times 1.75, close parenthesis, and I get 41.97. That's what I should get. That would conclude example 2. So we'll go ahead and look at our first word problem. So what distinguishes this one from the first set of problems is that it doesn't technically tell you what kind of value you're looking for, whether it's future or present. It just leaves everything kind of vague, and you have to determine all of that for yourself. So let's go ahead and see what we can determine from the context of the problem. So what will a $100,000 house cost 6 years from now? It sounds like the house is currently $100,000, and we're looking for what it's going to cost in the future. So if anything, that tells us we're looking for a future value, so one of these two, and we are compounding annually. So annual is a discrete compounding metric. So that tells us we would go down this column. Pretty much as long as it does not say continuous, we will use this column. And we already determined future value, so that leaves us at this formula right here. So I'll start by writing down the formula. And we can go ahead and write down the givens as well. So P P, R, N, and T. So the principal or present value seems to be the 100,000. The rate, that one's pretty straightforward, it's 3%, which is the same thing. Remember, we have to convert it to be a decimal. So divide 3 by 100, or move the decimal place over to the left twice. It's 0.03. The N corresponds to the compounding periods in a year. How many times does something annually happen in a year? That's just once. Also, again, I have all of them written down on the first page of this section's notes. And the time is 6, for simply 6 years. And with all of this information determined, we can go ahead and figure out what the future value is. So the P is 100,000. The rate is 0.03 divided by 1 raised to the 1 times 6. And from here, we just plug everything into the calculator as we see it, and we will be done. 100,000, open parentheses, 1 plus 0.03 divided by 1, close parentheses, raised to the 1 times 6. And I seem to get exactly this. And let's make sure that is correct. Yes, that seems good. Sometimes when I see students working this problem out, they'll get an answer that's really close to this, but their answer might be a decimal to the left or right. Normally the common mistake I see is people don't put enough zeros, or they put too many zeros, so just be a little bit cautious of that if you're getting the wrong answer. But other than that, that concludes example 3. So far you might think, all right, these problems have been pretty straightforward. I haven't seen one natural log yet, which is weird considering we've done quite a few sections on natural logs leading up to this. So this is the part that will distinguish the material we're talking about now from what you may have learned in Math 105. So notice they give you some amount. Someone has $100, so it sounds like that's a starting amount. They give a rate, they give the compounding cycles per year, and then they give the final value, or the future value. So they give you the present value and the future value, and it says how long, which really implies that we're looking for time here. So how long, that's an indication of time, and so this is where we're not going to be able to have a problem that's perfectly hashed out for us like we've had before. And so we do need to figure out which formula to start off with in order to start isolating for time, because each one of these has a t variable. Well, if anything, we don't have to do this in any particular order. Compounding monthly, that tells us that we would use one of these two formulas, and really it doesn't matter which formula we choose. We can use either one, we just have to use the one that corresponds to compounding monthly, as opposed to a continuous compound, which we'll do later. I like to pick the first one because there's not a negative on the t, so I'm going to pick this first one here. So that's a is equal to p 1 plus r over n raised to the n times t. And from here, we're going to start off the same way we have before. We're going to identify all of our givens and plug those in accordingly. So a here, a is 150, that's the final amount, which they give us over here. The principal value, or the present value, is $100. The rate seems to be 8%, which we'll go ahead and convert as 0.08. And compound monthly tells us 12 for n. And t, again, That's what we're looking for. We're looking for how long will it take for $100 to accrue interest enough to reach 150. So let's go ahead and plug everything in and see what happens. So now we have A as well, so that's 150. 150 is equal to P, which is 100. Open parentheses, 1 plus, the rate is 0.08, divided by n is 12, raised to the parentheses 12t. And again, we don't know what t is, so notice we have this equation and we're solving for t. This should seem very familiar to the previous section because there was a rule of thumb I gave in the previous section, which was what you do when the variable is stuck in the exponent. You have to consider the natural log. Now here, it would not make sense to apply the natural log right now. The reason why is because you have an exponential part right here. The 100 is not part of this exponent. So you need to bring the 100 over here, and then you can apply the natural log. So the first thing we'll do from here is divide both sides by 100. And that would get rid of the 100 over here. What we have now, so 150 divided by 100, that's 1.5. So now we have this. And I see this problem extending further than here. So let me erase that. So we're now to this stage, and now we have an exponential that's isolated, which means we now can apply the natural log, which is something you do whenever you have an exponential function and the variable is stuck in the exponent. So remember the process for that. It's simply applying the ln notation. So all I did was just add ln in front. I didn't do anything else. And that application of ln allows us to bring this exponent to the very front of the corresponding natural log, which now gives us exactly this. And if you're wondering why I didn't simplify the part in the parentheses, I looked at that and it gave this elongated decimal, and it's never good to round early in the problem. It'll mess up your numbers later on. So I'm keeping everything as exact as possible. That's why 150 divided by 100, I went ahead and just made that 1.5 because it's, well, a nice concrete number. This you get, I think, 0.666 repeated, and that's not exact. So this form should seem fairly similar to a form that we were at in the last section. In fact, what I did in that situation is I wrote t on the outside and wrote everything else on the inside to emphasize that the only thing you have to do to get t by itself, since that's multiplication, all you have to do is divide. And by dividing all of that stuff, you end up getting natural log of 1.5, all of that divided by parentheses, 12, natural log of 1 plus 0.08 divided by 12. And they do not want the exact answer. They do ask you to round to 2 decimal places, which does imply you need to be able to put this in your calculator. Now that's one reason why I kept the parentheses, is because if you don't put the parentheses in your calculator, it will split the 12 away from the natural log. That's why you need parentheses to hold it all together. So I'm going to type it exactly like this in my calculator. Natural log of 1.5 divided by, open parentheses, and I'll go ahead and type in 12 natural log, it opens one for me, 1 plus 0.08 divided by 12, close once, close again. And I get 5.09. And that is what we should get for this part of example 4. So the last part took a little bit longer than I expected, so I went ahead and just started over for part 2 of example 4. And this one, so the last problem, what we had was we had compounded monthly, and we did all of that work to solve for t. Now this says we're not compounding monthly, we're going to compound continuously, so it's still the same problem. So it's just saying, instead of monthly, we're going to switch to continuous and do the same thing. And it is nice to hear that this one's going to be a lot more simple than the previous one, although we're still solving for t. So here, since the compound's continuous, we're in this column, and we're solving for time, which tells us we can use either one of these. I like to use the one without the negative, the PERT formula, if you may. So go ahead and start off with that. So this is the formula we're going to use, and let's go ahead and write down the givens. So try a different marker. So the final amount, it did give us as 150, so that doesn't change. So in fact, nothing really changes except for the compounding cycles in a year. So this is still 100. The R is still 0.08. The time is still unknown. And for this one, we don't have an N because we're compounding continuously, which means we use the formula without the N. And from here, we can go ahead and plug everything in accordingly. So A is 150. P is 100, E is just E, 0.08 for R, and T is just T. So it starts off the same way. We have a problem and we need to get T by itself. We need the exponential part to be isolated, which means the 100 has to go. We're going to first divide both sides by 100. And so 150 divided by 100, that is in fact 1.5. So the same idea as before, we have a variable that is stuck in the exponent, and we have an exponential that's all isolated, which means we apply the natural log. So remember, that's just simply writing the ln notation to start off. So all I did was write ln in front. But what makes this problem work out nicer than the previous part, ln and e. You remember what those do? They cancel each other out. So the ln and the e, they cancel. And what we get is ln of 1.5 is equal to 0.08t, because that's all that remains over here. And all we have to do to get t by itself is divide both sides by 0.08. So now t is equal to ln of 1.5 divided by 0.08. again, they want a decimal approximation. So if you type this in your calculator directly, ln of 1.5 divided by 0.08, I get 5.07. And that would conclude both parts of example 4. So we'll go ahead and move on to another word problem. So this one, the problem says something about a survey that estimates the current cost of college to be some value per year. And for part A, it gives us this information about an 8.6 increase each year to the cost of college per year and what it will be in 12 years. So what we need to do is extract this information and see, well, as we've done for the previous problem, see which one of these formulas it fits. So luckily, they give us time, so that means we don't have to solve for time. So it seems like we're looking for a future value because it does say what will the average cost be. So if anything, we're looking for a future value, which means one of these two formulas, but you're looking for the compound, and it doesn't really say compounded continuously, monthly, semi-annually, because honestly they hid it. So it turns out they do give you the compounding cycles, they're just not saying it in the wording that we're used to. In fact, you might be looking at this and think, well, where are they saying it at? They say it right here. They say each year. So if something's increasing each year, that means it's happening annually. So this is a fancy way of them saying compound annually. So they do actually say it just implicitly, which does tell us that we would use this formula because it's the non-continuous formula. So let's go ahead and write down that formula. And we can also go ahead and write down our givens. So P, R, N, and T. So the principal here is the starting value. That will refer to the starting value of college per year. So that is the 34,630. The rate, we're going to go ahead and convert the rate to a decimal, which is 0.086. We move the decimal place over to the left 2 times. The N, that refers to the compounding cycles in a year. Compound annually is 1 cycle in a year. And the time refers to 12 years. So now that we have all of this, we can go ahead and plug in everything and solve for A as we've done before. So that is 34630 parentheses 1 plus 0.086 divided by 1. All of that raised to the 1 times 12. And fortunate for us, it's just a calculator problem. We don't have to isolate anything. So as we've done before, I get 93,198. Is that what I should get? Seems good. So 93,198.82. And again, we're rounding to the nearest cent, so we'll go ahead and bump up the 8.1 to an 8.2 because there's a 5 after it. And so that would answer part A. Now part B says if this rate of 6.7% compounded continuously is offered, how much should be put into the plan now to prepare for this price of 1 year for college? So again, we have to figure out, extracting all this information, which formula does this most closely associate with? Now, if anything, they tell us compound continuously, so that means we're on this row. And so one of the indications here, how much should be put in now? So now here seems to be a good keyword to imply that we're looking for the present value. So continuous compounding, present value, we use exactly this formula. And so let's go ahead and again write out what our givens are. So here A is the future value, and what that's referring to, so what 1 year of college will cost in 12 years. So it turns out it's referring to the value we found in part A. So we actually just found this value in part A. So we're going to recycle that value. It's the 93,198.82 that we found right here. The rate is the 6.7%, which we'll go ahead and convert to a decimal. And the time is still 12. They even emphasize it at the bottom here, for 12 years. And with all of this information determined, we can now plug in everything accordingly and solve for P. So 93,198.82. E is still E. Open parentheses, don't forget the negative. 0.067 times 12. And if you did everything correctly, you should get 0.82 E negative 0.067 times 12, close parentheses, and I get 41709.76. And that would conclude example 5. So finally, we'll move on to the last question from the homework, which is, well, we're looking for the rate of interest. So we're looking for the rate. And that makes sense because we've solved for A, P, and T. We don't really solve for compound cycles in this class, but the rate is something we will solve for here. And this problem is mainly a precursor towards the final section, actually for the class, which is on exponential growth and decay. But in this problem, we're looking for the rate of interest and something about double an investment in 20 years. So they give us some vague information. If anything, they give us compound annually. We're going to go back to figuring out what formula that this corresponds to. Compound annually tells us that this is a discrete compounding problem. So it's going to be one of these two. And we're not looking for a future value, nor are we looking for a present value. So just like with the time-based problems, I'm going to select this formula right here. So this one seems to be A, P, 1 plus R over N raised to the NT. So from here, we're not really given too much. The only things that I see explicitly is that N is equal to 1 because we're compounding annually, and that T is 20. They also give us information about A and P together. So remember, P is the present value, A is the future value. And here, it actually gives you a lot more information than you think. Here it's saying the investment will double. So it's saying if you were to put in maybe $20, then double that, that's $40. If you put in $100, double that, that's $200. So what it's saying here implicitly is that the quotient of A divided by P, the future value divided by the original value, this here is equal to 2. And that makes sense because the future value is 40, the present value is 20, that's 2. If the future value is, say, 500 and the present value is 250, their quotient is still 2. No matter what numbers you pick, as long as the numerator is double the denominator, this is 2. So that's actually another bit of information that they give us down here. And so you might think, all right, how does that help us? Well, let's go ahead and plug in what we do know and go from there. So A, we'll keep A as A and P as P. So that's 1 plus the rate, which we don't know, divided by 20, well not 20, sorry, divided by 1, all of that raised to the 1 times 20. So this is what we get after we do all of that. Now, we do have an exponential function. It is true that we do not have a variable in the exponent, but we do have a variable in the base of an exponential, which I'm trying to find a way to motivate this quotient over here, because we can divide both sides by p, and we actually did this for time when we solved for time. So we're going to do the same thing here. It's just instead of an actual number, we're dividing p on both sides. And then we have this a divided by p, which I mentioned over here is 2. So now we have 2 is equal to 1 plus r raised to the 20th power. And I did clean up some things over here on the right hand side. So r divided by 1 is just r, 1 times 20 is just 20. So now we're here, and from here we're still trying to get r by itself. So one thing we can do is we don't have to use the natural log here, because the variable is not in the exponent. Instead, we can take the 20th root. So if this was 1 plus r squared, we could take the square root on both sides. Instead, it's the 20th root. So here, we're taking the 20th root. The 20th root of 2 is equal to 1 plus r. So that's how we're transitioning here. Technically, we would need a plus or minus, but remember the rate is a positive value. We have positive rate. So we're going to ignore the negative value of this. And so all we have to do is subtract 1 on both sides to get r by itself. So r is equal to the 20th root of 2 minus 1. And they do want us to, again, round this to 2 decimal places. So 20th root, that means you do need to know how to put the 20th root in your calculator. Minus 1. And you should get 0.0, and I'm going to write out a few of these. So it goes on seemingly without end. But remember, rate is a percentage. Normally we convert the percentage to a decimal, but now we need to go backwards. We need to convert this to a percent. And so that means we have to move the decimal place 2 places to the right. So that's going to be 3.53, because it wants 2 decimal places. So this one is definitely a little bit trickier. That's why I wanted to show you all it, but it's the only one like this on the homework, and it does motivate the next section. But other than that, this would conclude this lecture.